Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone, it's my great pleasure to welcome Z Huang back. Z has been an intern here before, twice actually, and he got his PhD from UPenn, spent a year at Stanford as postdoc, and is now a professor at the University of Hong Kong. And he's going to tell us how to make the most of our samples, which I think is really important. So, over to Z. Okay.
Okay, thanks for the introduction and thanks for coming. So this is a joint work with Yishai and team, and it's a paper that's in coming easy. So we're going to talk about auctions and talk about revenue maximization in auctions. So basically, auction is about allocating a bunch of resources to agents in some specific way, following some protocols to satisfy optimize certain objective, and the two most studied and natural objectives in auction are social welfare, namely kind of the overall happiness of all the agents, and the second one is just revenue maximization, like making more money out of the sale of items. So you can find tons of real-life applications where revenue is a natural objective, say at auctions, at Microsoft Bing or Google, or those auctions on eBay and so on. So roughly speaking, there are two ways to get good revenue out of selling items, right? One is from the competition of these agents, potential buyers. If their kind of value for the items are somewhat close to each other, the competition is high, then just let them compete with each other and like use the second price also will give you good revenue. But sometimes maybe only one agent has high value for the item, in which case there's not enough competition, and in which case the usual practice is to use reserve prices to get good revenue. Okay? And the good things about using reserve prices is they are simple and natural, and also it's simple for the auctioneer to implement the auction, and also easy for the buyer to figure out what's going on and what they should behave, right? And also it's kind of optimal in many settings. So classical result by Meisen back in the 1980s shows that victory auction or the second price auction combined with a reserve price is actually optimal for selling a single item, assuming these agents' values are drawn i.i.d. from some public known distribution. So since using reserve prices to maximize revenue is natural and sometimes optimal, so a very important question is how to set reserve prices. So here's sort of the very basics of how to set reserve prices. So consider the following the most basic scenario. We have one item for sale and only one potential buyer. And his value is drawn from some publicly known distribution denoted as F. So arguably the most simple setting you can consider in terms of revenue maximization. And given any price P, we are going to let Q of P to denote the quantile, and in this case, just 1 minus the CDF of P. This is the sale probability. And then the revenue of a certain quantile is just the revenue we can get by setting the price to be the value at that quantile. So it's V of Q times Q. Okay. So we're going to adopt some standard assumptions from economic that the distribution satisfies some regularity condition. For now, just imagine that as having this revenue curve in terms of the function of quantile to be a concave function. And then now since this function is concave, well, we can easily find the maximizer of this function, which would correspond to quantile and the corresponding price that we should use if we want to maximize revenue. Okay, so here's all very nice and simple, but that leaves a very important question. Where do these Bayesian prior come from? So in the literature, usually we just assume that magically we have some closed form like description of this prior, and then suppose we have those closed form descriptions, then we just like do the magic and come up with these optimal prices, right? So, but in practice, these priors do not come for free. So where do they come from? One obvious answer, which is a valid answer, is from the data of past user behavior. Say at auction, we have tons of past behavior, and people submit bids in the past, and if you kind of assume they are kind of behaving the same and having the same distribution across different time span, across different day, then we have certain knowledge about this price distribution, okay? However, it's not clear, like given this past user behavior, it's not clear using this optimal reserve, like from some kind of empirical distribution from this data, is actually approximately optimal for the true prior, okay? And also, this past data do not give you any kind of a closed form description. No one's going to tell you that, okay, this is a uniform between 0, 1 or something like that, okay? They only give you some samples from the prior, even in the most optimistic case. So it seems that a more practical model would be, like we're given some i.i.d. samples from the prior, and now I want to choose a reserve price based on these samples. And again, we want to approximately maximize the revenue, okay? So this is the model that we are going to focus on in this talk. Okay, so more formally, a M pricing algorithm will take M i.i.d. samples from the prior as input and output some reserve price. And then we will consider its approximation ratio as the expected revenue we can get from this algorithm over the random realization of these samples. And compare this with the optimal revenue you can get in hindsight choosing the absolute optimal reserve price. And this is the approximation ratio of the algorithm. And we want to make this as large as possible, obviously. And there are multiple ways we can ask this question. For example, given a fixed number of samples, what pricing algorithm gives the best approximation ratio? Okay? So in some sense, how this is being done in practice is that we take these samples and we pretend that the underlying distribution is just a uniform over these samples. And then based on this empirical distribution, we try to choose the best possible price. And maybe some hack on the empirical distribution as well, but that's essentially what's being done. But is that the best thing to do? And more importantly, if the number of samples are small and you don't get to form such an empirical distribution and good approximation of the prior, how are we going to get good approximation ratio? And secondly, we can also ask this question in terms of kind of a sample complexity style. So given a target approximation ratio, how many samples does this optimal algorithm need in order to achieve that target approximation ratio? Okay? And surprisingly, even these very basic questions, and for the very basic setting of a single agent, a single item, largely we don't know the right answer. Okay? We have some kind of upper and lower bound, but there's pretty large gap between them, and we don't know the right answer.
So there, like, so it's
yeah.
Basically single buyer, single seller. Do you have a prior or no? You're saying there's no prior now. You just take
So we have a prior, but it's not given to the algorithm in closed form. We can only access the prior through this i.i.d. sample. Okay, so we assume the existence of a prior, but we do not know where it is, other than those samples we get. Okay. Okay.
If you know the distribution.
Oh, we don't know the distribution.
How do you know the distribution?
Yeah, then it's Myerson.
Yeah.
It's just Myerson.
Yeah, it's just Myerson.
But like, okay, I guess if you can, for example, take just one sample.
Right.
Like, isn't the algorithm clear what the right algorithm is? I just take the
sample. So there's some result for that.
Set it at reserve price. What else to do?
Yeah, so actually,
is there a better
the best
paper
deterministic one, but this is the paper that shows there's a better randomized one.
And for special class of distributions, you can do better than setting that.
No, but that's what I'm asking. Then now you're saying you assume something about a distribution. What I'm saying is, I don't assume.
If you assume nothing, then you have to set that whatever sample you have as the reserve price. That's it.
No, usually you assume like
if it's not regular.
And even for that, regularity is necessary.
Even on that.
Even for that, regularity.
So that's what I'm saying. Like, you should assume something that you know about the distribution. It's some certain class.
Oh, okay. So, yeah, there's some restrictions, some regularity assumptions on the distribution that's needed. So that's for sure. But other than that, we don't know anything about the distribution. So we know that, for example, we shouldn't be like targeting a epsilon sale probability and all the revenue just come from that small probability. Like for that, basically so here's a kind of potential bad distribution, right? So if you have probability 1 over h, the value is h for some very large h, and then otherwise the value is just 0, then you cannot expect to have kind of anything good, right? So some kind of regularity, kind of small tail assumption is needed, but other than that, we don't have any knowledge of the distribution. Okay. Okay, so again, we're going to ask the question in the following ways and in different regimes. So for the sample complexity, obviously we will ask in the asymptotic regime, assuming we have access to many, many samples, and all we want to know is how many samples sufficient and necessary to get 1 minus epsilon approximation. And in terms of the algorithm question, we are going to ask this question in the few sample regime, because if we have many samples, in some sense, the algorithm is clear, right? You kind of want to use those samples and form some empirical distribution, and at least when the number of samples go to infinity, that's the right answer, right? But with only a few samples, now what's the right algorithm? That's not clear. So that's also the question that we're trying to ask. And now we get to the regularity assumption that we're making about the algorithm. So there are 2 common assumptions in the literature. One is called kind of regular distribution. There's some technical definition saying that the virtual value defined in this way is non-decreasing as a function of the value v. Okay, but really it's just saying that the revenue curve, kind of this R of Q on the quantile space is a concave function. Okay. And there's more restrictive assumption called MHR. So the prior has monotone Hess array. Again, there's a technical assumption like this guy is non-decreasing. But for now, let's assume that it's just saying that the revenue curve is strictly concave in some sense. We will get to the point like in what sense it's strictly concave later in the talk.
So just one thing. So virtual value. So is there an intuition to that expression b minus? Why do they call it virtual?
So it kind of comes from this Meisson's analysis on revenue maximization. It's kind of how much revenue you can get if you sell the item to an agent with this value, basically. But like roughly speaking, yeah, using second price, yeah. Okay.
For any truthful mechanism, the expected payment for the distribution, draw from a distribution, the expected payment of an agent is something like this. The expected payment is expected virtual surplus basically. The payment is some second order. It's not something directly given to you. So instead of counting payments, it's another way of counting revenue, which is counting virtual value for each value point in the distribution. So if you add all these, you get revenue. That's it. Yeah. So yeah, instead of maximizing value, you maximize this. Is equal to maximizing revenue.
Okay. Okay, so basically we're going to do some combination of these 2, like few sample and this asymptotic regime and regular and MHR regime. Okay. Okay, so we're going to go over what we know about this problem across these different regimes and kind of go over what our results are, and then depending on how much time I have, I'll go over some of the proof sketches. So first of all, let's look at the asymptotic regime. So again, we have many samples, and we want to know how many samples is sufficient and necessary in order to get 1 minus epsilon approximation. So this has been studied before. So we know that, Davenota et al. Proposed this empirical reserve algorithm, which is what you would expect. So given m samples, v1 to vm, so I times vi is basically the revenue you could get, assuming like the underlying distribution is just a uniform over v1 to vm. Okay, so it should just take the argmax of this. Except there's one caveat, so it's called the alpha guarded empirical reserve because it will rule out the alpha fraction, largest fraction of the value. Okay, so in terms of kind of a machine learning kind of perspective, it's try to prevent overfitting because if the argmax is actually one of those VI that are in the alpha largest fraction, then basically your revenue is coming from very small fraction of the sample, right? So maybe you're overfitting to that very small fraction of the sample, which may not be a good thing, okay? So basically, you choose alpha to be something like epsilon, and then you use this algorithm. And what they show is that the epsilon guarded empirical reserve with 1 over epsilon cubed samples is sufficient to get 1 minus epsilon approximation for regular distributions. Okay? Yep.
So if I take so many samples,
Right.
And I look at the empirical distribution,
Okay.
how far will it be away from, let's say, in like total variation distance from the real distribution? Because in some sense, one thing to do is I'll just learn the real distribution, right?
Yeah, but
So just to make a comparison.
but we need to make sure be careful to define the distance. If you take total variance, then the total variance could be just 1, right? Because it's a discrete distribution and so on.
Yeah. So let me, maybe some other distance. I don't know what this is.
Yeah. So in some sense, at least for the purpose of getting good revenue, it's close enough, obviously. And other than total variance distribution, I'm not sure what would be a good measure to measure distance between a discrete distribution and the potentially continuous underlying distribution, right? So I guess what I want to say is that I don't have a good measure of distance off the top of my head for measuring like the empirical distribution and true underlying distribution for this case. But but at least they show that it's sufficient for like getting good revenue. Okay, and for the more restricted MHR distributions, they show that 1 over epsilon squared samples is enough, and also you don't need those to put the alpha guarded version. You just use the empirical optimal price, and then that's 1 minus epsilon approximation. Okay, and yeah, sure.
This goes against what you just said, right? You said it makes logical sense to guard.
Yeah, it makes logical sense to guard if it could be possible that like one of these guys, that one of these very high value are the argmax, right?
Okay,
but MHR basically is a stronger small tail distribution, and then it's unlikely those will fool the algorithm. Okay. Okay, and more recently, there's a paper by Cole and Roughgarden that studied essentially the same setting, but in a more complicated scenario where we also have a single item for sale, but we have k bidders instead of only one bidder. And these k bidders' prior distribution may not be identical. Okay, and their main result is that the sample complexity has to be polynomial in the number of bidders k. Okay, and so in terms of the dependency on epsilon, all they show is that it's something like 1 over epsilon, square root of epsilon. So pretty far from those upper bound from the previous paper. Okay. So what do we get in this work?
So in this, that is for each distribution.
Yeah, for each distribution. So in their model, basically, in each round, you get 1 sample for each buyer, and they're saying that the number of rounds you need to be polynomial in k. Okay. So you need more fine-grained knowledge about the distribution if you have non-identical bidders. So on the algorithmic side, we give a improved MHR upper bound. We show that using the same algorithm, actually 1 over epsilon to the 1.5 is enough to get 1 minus epsilon approximation ratio. And we also show matching lower bound. Actually, we give a lower bound framework, and we show that 1 over epsilon to the 1.5 is the right answer for MHR distributions, and 1 over epsilon cubed, which is achieved by this previous analysis, is also tight. And this is borrowing some techniques from information theory and differential privacy. And I would like to kind of say a few more words about these results for MHR regime, because it's kind of surprising, at least to me. So first of all, when we first get this result, we think something is wrong with our analysis. And Yishai was saying like 3/2 should not be the right answer for anything, especially in terms of like sample complexity. It's very rare you see something like that. And also, noticeably, this is fewer sample than what you would need in order to estimate the optimal revenue up to a 1 minus epsilon factor. So even if I tell you what is the optimal reserve price, you basically need 1 over epsilon square samples to estimate the optimal revenue up to a 1 plus minus epsilon factor, right? Basically, you want to estimate the sale probability, and in order to estimate that to a 1 minus epsilon factor, you need 1 over epsilon square samples, okay? So in this sense, using this many samples, we don't quite know what the optimal revenue we get, but we know what is a good price, okay? So kind of the optimization version is easier than just estimating the objective. And we'll see some intuition why this is possible. Now, for now, let me also go over some of the results for the single sample regime. So this is a classic paper by Blow and Klemperer. And they basically shows that if you have one sample and you use that sample as your reserve price, then this is 1/2 approximation, assuming the distribution is regular. And for the more restricted MHR version, basically no result is known prior to our work. People just plug in this 1/2. So what we show is that actually you can do better for MHR distribution. If you take the sample and scale it down by some factor, 0.85 in this case, then you can actually do a 0.589 approximation for MHR distribution. Okay. And we also show some upper bound, like 0.68 for MHR distribution. And we also show that this 1/2 approximation for the regular distribution is tight for deterministic algorithms.
That's for equal revenue.
Yes. Yeah, kind of equal revenue type of distributions. Yep. Okay. And moreover, like our positive results also have implications for more complicated setting, like the multi-agent problem, because some of these multi-agent results use the single agent as a subroutine and do some direct reduction. So we know that if we have some good pricing algorithm for the single agent problem, then there's a way to convert them to multi-agent problem as well. So for example, we can combine our results with the results by Yamamoto et al. So what they show is that for what they call prior independent auction in the matrix environment with i.i.d. MHR bidders, then they can do n-1 over n times 0.5 approximation. And we can directly plug in our new results and improve that 0.5 to 0.589. And similarly for the other results as well. And asymptotically, we can also plug in our new sample complexity upper bound and improve the number of bidders they need to get 1 minus epsilon approximation from 1 over epsilon cubed to 1 over epsilon 5/2. And yeah, there's a more recent result by Tim and his student. Also use the single agent problem subroutine, and we can also plug in our new results to improve some of their ratios. Okay, so now let me get to the technical part and kind of sketch some of the high-level ideas behind these results. So let's first consider the asymptotic and MHR regime and explain why we managed to get this weird 1 over epsilon to the 3/2 upper bound. So first of all, let me briefly go over what's the usual sample complexity upper bound technique. So, so consider the empirical reserve price algorithm. We take these samples and we just use that as an empirical distribution and pick the best price. The high-level plan would be, I want to estimate the revenue or the sale probability of each potential price, namely these VIs, up to a 1 minus epsilon factor, like use some concentration bound and so on. And then we show that if we can do that, then choosing the best from this empirical distribution would be a 1 minus epsilon approximation. And small quantile could be problematic, as I just explained, and that's the intuition behind dropping the epsilon highest value and use this epsilon guarded version. And with 1 over epsilon cubed samples and also concavity of the revenue curve, we can achieve exactly that. So first of all, by concavity of the revenue curve, we can see that it's okay to drop the highest value because in this revenue curve, it drops at least as fast as linearly, right? So just dropping an epsilon fraction in the quantile space does not hurt your optimal revenue by more than a 1 minus epsilon factor. And second of all, since for any candidate price that we consider in the epsilon guarded version, the sale probability is at least epsilon. So with 1 over epsilon cube samples, we expect to see at least 1 over epsilon square samples that are larger, right? So that will allow us to estimate the sale probability of every single price up to a 1 minus epsilon factor just by simple application of the Chernoff bound. Okay? And that's enough to finish the proof of this 1 over epsilon cube upper bound, sample complexity upper bound, or for regular distribution. Now for MHR, it's pretty much the same thing, except that we will use a simple property of MHR distribution that the optimal sale probability is at least some constant 1 over E. And that's also a standard result in the literature. And then it's the same argument, except that now the relevant prices have sale probability at least a constant. So with 1 over epsilon square samples, you expect to see 1 over epsilon like sales, right? And that's enough to estimate the sale probability up to 1 minus epsilon. Okay? So that's how you get the 1 over epsilon square upper bound. So all very straightforward. And just from this analysis, you may think that 1 over epsilon square is the right answer. So why is that? Okay, so what could be a potential best scenario here? So maybe there's some other price, P, other than P star, who is only a 1 minus 2 epsilon approximation. But somehow, due to sampling error, you overestimate the revenue of this price by a 1 plus epsilon factor, and maybe also underestimate the revenue of the optimal price by a 1 minus epsilon factor. And as a result, the algorithm mistakenly picked this price over the optimal price, right? And indeed, this could happen if this sale event are treated as two independent conflicts, and then you want to see which one is larger. But the problem here, what's missing here is that these two events are not independent. So when we try to estimate the revenue of these prices, there are correlations. Okay? So take this as an example. Suppose Q star is the optimal price, the quantile of the optimal price, and Qi is the quantile of some other prices. So basically what we want to estimate is the number of samples that fall between 0 and Qi and the number of samples that fall between 0 and Q star, right? So you can see that the number of samples fall between 0 and Qi basically contribute to the sale probability of both. Okay? So there's some kind of correlation here. And in particular, kind of overestimated the sale probability or the revenue of Qi doesn't matter that much because those will contribute to the sale probability of Q star as well. So if you have more sample here, then you overestimate both. Okay? The error mainly comes from the samples that falls between Qi and Q star. Okay? And that observation will allow us to do a better analysis. So, okay, so that's the high-level intuition why we might be able to do a better analysis. Now let me get to the technical part. So we will need a technical lemma. So recall that when I say the MHR distributions, the MHR assumption can be interpreted as saying the revenue curve is strictly concave. Now this lemma will tell you that it's actually strictly concave, at least at the optimal price. So it's saying that when we move away from the optimal price in the quantile space, then the revenue drops at least quadratically as how far we move away in the quantile space. So here's the intuition. There's some technical definition for MHR in terms of this virtual value and so on, but you can also play with it and write it as a differential inequality about the revenue function over the quantile space. So it's just this guy. And then now let me explain how to interpret this. So on the left-hand side, I have the kind of a second order derivative of the revenue function on the quantile space. And on the right-hand side, it's basically saying that how kind of a lower bound on the magnitude. So it's saying that it's negative, and the right-hand side tells you how negative it is. So what is this R of Q minus Q of R prime of Q? It's basically taking tangent line at Q on the revenue curve and consider this intersection with the R axis. And then the length of this intersection is exactly R of Q minus Q times R prime of Q, right? So basically, the right-hand side is saying that the magnitude of this second order derivative is at least as large as the intersection with the r-axis by this tangent line. It's not exactly the differential thing, but yeah, I do think it's kind of similar.
It's the same if you think of it as a function of.
Yeah, in some sense, yeah. But yeah, but in any case, like using the fact that q is between 0 and 1, it's saying that like the second order derivative is at least as small as like minus the intersection of this length, the length of this intersection. And in particular, if you like take q to be q star, then this tangent line is a kind of a flat line, and then the intersection is simply the optimal revenue, right? Okay, so it's saying that the second order derivative and q star is at least as small as negative rq star. And then at this point, the first order derivative is 0, right? Because that's the definition of being optimal. Now,
More similar to strong concavity.
yeah, it's kind of strong concavity at this particular point. Okay. Now, kind of the intuition that Taylor expansion tells you is that now R of Q kind of drops at least quadratically with this form. Okay. Now, of course, Taylor expansion only tells you this holds in a small neighborhood of Q star, and we need this for any Q. So the actual proof is more complicated, but at least this is the intuition behind this. Okay. Okay, so given this technical lemma, now we are ready to show this 1 over epsilon to the 3/2 upper bound. So we're given these samples, and for simplicity, let's assume that the optimal price is also in the sample. We pick between them. So what we want to show is that for any sample VI with quantile, let's say QI smaller than Q star, and revenue, which is a 1 minus epsilon approximation of the optimal, we want to show that any of such VI cannot fool the algorithm, will not fool the algorithm with high probability. Okay. Now, in general, of course, it may not be exactly 1 minus epsilon, but this seems to be the worst case scenario, right? It's the closest.
So this is a bad.
Yeah, this is a bad event. I want to show that this bad event cannot happen with high probability. Okay, so what does it mean that VI fools the algorithm, or the algorithm picks VI over the optimal price P star? It's basically saying that how much we underestimate the sale probability of the optimal price is at least 1 minus epsilon times more than how much we underestimate the sale probability of VI, right? It's this. So now if you kind of move around the terms and so on, and also recall this picture, basically all the error basically comes from the number of samples that fall between QI and Q star, right? Because the number of samples fall between 0 and QI kind of contribute to both, and then they do not really matter. At least they do not matter in the first order sense. Okay, so if you play this out, that basically means that the number of samples that fall between QI and Q star must be very small, and it's at least epsilon m. It's smaller than its expectation by at least epsilon times m, basically. Okay. So this is because in order to underestimate the sale probability of V star, we need the number of samples that fall between QI and Q star to produce an error that's kind of at least an epsilon fraction of the total number of samples that we expect to fall between 0 and Q star. And that number is at least kind of order 1 times m, because the optimal sale probability is at least 1 over e, right? Okay. So we have some lower bound in how much error we expect to see kind of in this small interval. So what we need next is an upper bound on how large this interval is. And that's where the technical lemma comes in handy. So the technical lemma says that when we move away from the optimal quantile, then the revenue drops at least quadratically. And since this revenue is 1 minus epsilon times the optimal, that means this interval cannot be larger than roughly square root of epsilon, right? Okay, so we have some upper bound on the size of this interval, and we also have some lower bound on how much additive error we expect from this interval. And now it's just simple application of the Chernoff bound. And that which tells you that with 1 over epsilon to the 3/2 samples, well, with high probability, this cannot happen. Okay?
So you're using this 1 over e fact about MHR distributions here, right? And
Sorry?
you're using this 1 over e space left for MHR distributions here, right? That if you sell, there's a probability of accepting yes at least.
Yes, I'm using the fact that basically Q star is at least 1 over e.
Right. So do you also do something for alpha regular distribution in this paper?
Yeah, good. There's a kind of a family of assumptions that kind of interpolate between MHR and regular proposed by team recently called alpha strongly regular distributions. So for alpha strongly regular distributions, again, the right answer is 1 over epsilon to the 3/2, but the constant kind of becomes worse as alpha goes to 0. Okay, so kind of the regular case is a singularity point when alpha goes to 0.
Asymptotically, it's still 3 over 2, just like.
The dependency on epsilon is still,
Okay,
1 over
that's
epsilon to
what I
the
was asking.
3 over 2.
Given this
Yeah.
is what you're using. It's
Okay.
okay.
And like, both upper and lower bound. But in that case, the both upper and lower bound does not match in terms of the dependency on alpha. At least for our current analysis, they do not match. But still, the dependency on epsilon is 1 over epsilon 3/2. Okay, so that's the upper bound. So again, basically, it's just exploiting the fact that when we estimate the revenue or sale probability of these different samples, there are correlations, and this correlation is helping us. And basically, although we don't quite estimate the revenue up to a 1 minus epsilon accuracy, but that does not matter. When we overestimate everything, and when we underestimate everything. What matters is the kind of a relative relationship of this expected revenue that we estimate, and 1 over epsilon to the 3/2 is enough in that perspective. Okay, so now let me try to explain the lower bound framework. So at a high level, we are trying to reduce the sample complexity of this revenue maximization problem to the sample complexity of a classification problem. So suppose we have two prior distributions, D1 and D2. Both are regular or both are MHR, depending on which setting we are talking about. And suppose they are different enough in the sense that they have disjoint 1 minus epsilon, a 3 epsilon optimal price set. So what does that mean? It means that for any price, if it's 1 minus 3 epsilon approximation for D1, then it cannot be a 1 minus 3 epsilon approximation for D2 simultaneously, and vice versa. Okay? Now, if this is the case, then any pricing algorithm that is 1 minus epsilon approximation for both D1 and D2 will effectively distinguish these two distributions. So basically, you run the algorithm on the samples, and then you see what's the price that is suggested. And if the price is suggested fall into this 1 minus 3 epsilon optimum price of D1, then you kind of assert that the underlying distribution is D1, otherwise you say it's D2. And if the algorithm is good, then you will succeed with high probability. Okay? So effectively, a good pricing algorithm can distinguish these two distributions. So the high-level plan is to construct these two distributions to be as similar as possible, subject to having disjoint approximately optimal price sets, and then use tools from information theory to lower bound the number of samples we need to distinguish these two distributions, and that would translate to a sample complexity for the kind of a revenue pricing algorithm. Okay, so many of you may be familiar with this, but let me go over this anyway to make sure we're on the same page. Just some information theory basics. So when it comes to distinguishing two distributions, we need some measure of distance of the two distribution, and turns out the right notion of distance here is the statistical distance defined in the first line. And basically, if you want to distinguish these two distributions with probability significantly higher than 1/2, then the statistical distance between the two distributions has to be at least as large as some constant. Okay, so that's the takeaway point from this. And in our case, what is P1 and P2? P1 and P2 will be the joint distribution of kind of i.i.d samples from D1 and D2 that we talk about, right? And usually it's kind of pretty hard to handle or compute the statistical distance of these kind of distributions, and that's why in the literature usually people use KL divergence instead. So the definition of KL divergence is in the second line, and KL divergence and statistical distance are related to each other by what's called the Pinska's inequality. So the Pinska inequality basically says that if the statistical distance is at least a constant, then the KL divergence must also be at least as large as some constant. Okay? And the nice thing about KL divergence is that if you take m.i.d samples, then the KL divergence just get multiplied by m. Okay? And so in order to show that the KL divergence of P1 and P2 is small, it suffices to show that the KL divergence of the kind of base distribution D1 and D2 is small. Okay? Okay, so now, if we can distinguish, we have a good pricing algorithm using only m sample, that means we can distinguish D1 and D2 using m sample. It means that the KL divergence between kind of D1 to the m and D2 to the m is at least as large as a constant. Okay? Now, that means that the KL divergence between D1 and D2 must be at least as large as some constant over m, and the sample complexity. On the flip side, it says that the sample complexity has to be at least as large as 1 over the KL divergence of the D1 and D2 that we construct, right? Okay. So now the plan is to construct two distributions that have disjoint approximately optimal price set that has small KL divergence. Okay? And when it comes to construct distributions with small KL divergence, we use some lemma from the differential privacy literature. So it's basically saying that if pointwise the density function differs by no more than 1 plus minus epsilon factor, then the KL divergence is at most epsilon squared. Okay? So kind of the KL divergence is just the expectation of the log of this ratio, right? So the fact that this ratio is between 1 plus minus epsilon basically say that the log is at most epsilon. So the trivial analysis will give you that the KL divergence is at most epsilon. So why epsilon squared? So the observation is that like these signals or samples that you get not only give you kind of positive signal, but also give you false negative signals. Okay, so for example, like if two distributions are very, very similar, then when you get one sample and you say that the density of D1 for this sample is larger than the density of D2, you assert that it's more likely the underlying is D1, right? But it's possible that this underlying sample is actually from D2 and you're getting some kind of false negatives, right? And kind of mathematically, it's saying that since D1 and D2 both sum to 1, it cannot be all these ratios are 1 plus epsilon. A lot of them will be 1 minus epsilon as well, and therefore, basically the first order term will cancel out and only the second order term will remain, and then you get kind of epsilon squared, okay? All right, in any case, so now the goal is to construct these two distributions such that pointwise their density is kind of close to each other while keeping the approximately optimal price at disjoint. Okay, so I will not bug you with the kind of mathematical verification that they actually satisfy those conditions, but I'll kind of tell you what the distribution look like in terms of the revenue curve. Okay, so for regular distribution, we are going to consider the following two distributions. So the first distribution is what's sometimes called an equal revenue curve. So it's the blue line, basically a straight line, the triangle that peak at quantile q equals 0. And the second distribution is essentially the same, except that we truncate it a little bit at the high quantile regime. Okay. So kind of from the picture, you can see the two distributions are very similar. but also the kind of 1 minus epsilon approximate price set are disjoint, because the approximate price set for D1 is essentially the blue area, and the approximate price set for D2 is essentially the red area, right? Now, if you calculate the KL divergence of these two distributions, then kind of for a majority of the samples in the quantile space, the densities are identical. So only for the kind of top 2 epsilon 0 quantiles, their densities are different. And even for that kind of a small fraction of the samples that they are different, they differ by at most 1 plus minus epsilon factor, and overall you get that the KL divergence is as small as like epsilon cube. Okay, so that's how you get the 1 over epsilon cube sample complexity lower bound. And for MHR, again, very similar thing. You kind of construct two things that kind of shift a little bit such that their price sets are disjoint, and then show that their KL divergence is small. And the distribution we consider, the first one is kind of a uniform distribution between 1 and 2. And the second distribution, we basically kind of scale down the density between 1 and 1 plus square root of epsilon by a little bit, and then scaled up the density in the rest of the value space by 1 plus epsilon factor. And it turns out that's enough to shift the distribution enough to have disjoint price space, and then the KL divergence turns out to be epsilon to the 3/2. Okay. Okay, so that's all the results for the asymptotic regime. And now let me spend. When should I stop?
5 minutes.
Oh, 5 minutes? Okay. Okay, so I'll give a very high-level view of why, kind of in a single sample space, we get better than 0.5. So how do we prove 0.5? It's actually very simple, okay? So recall that regularity means that the revenue curve is concave, right? And if we use the identity pricing, meaning that we take a sample and just use it as the reserve price, then the expected revenue you get is exactly the area under the revenue curve, okay? Because you take a sample, then the revenue you get for that sample is just the height in that quantile space, right? And then you take expectation, just the area under the curve. And it's concave, so this area is at least as large as the area of this triangle that peak at the optimal. Now it's basic geometry, right? So what's the area of this triangle? It's the height, which is r star, times the base, which is 1, and then divided by 2. And therefore, the expected revenue is at least optimal over 2. Okay? So since in some sense, MHR distributions are strictly make this revenue curve strictly concave, that kind of suggests that identity pricing will get strictly better than 1/2. But that's not quite the case, because it's not strictly concave in the usual sense. Okay? So kind of this is a technical definition, and it basically says that for the quantiles that are larger than Q star, meaning for the values that are smaller than the optimal price, indeed, this is strictly concave. And in fact, we can show that it's at least as concave as the revenue curve of exponential distribution. Okay? However, for the first half in the quantile space, not necessarily. And in particular, we can kind of truncate any regular distribution, which means that we kind of flatten that to be a straight line. And that's still a regular distribution, and that part is not strictly concave. And in fact, a point mass is a regular distribution, and for a point mass, identity pricing only gives you 1/2 of the optimal, right? Okay, so now for the so not exactly point mass. Let's say a uniform distribution between 1 and 1 plus epsilon for very small epsilon. Then basically, the revenue per sale is 1, right? But the sale probability for identity pricing is only 1/2.
Right, okay.
Yeah, kind of a point mass, but you kind of play with it a little bit.
I see you've written it.
Yeah. So so it seems like, okay, so the takeaway point is this. For MHR distribution, the revenue curve looks like something as concave as exponential plus some truncation at the beginning. So let's say that's the case, and let me explain how to get around this and how to get better than 0.5. So the hard part is the truncation part, right? Because for that part, identical pricing gets exactly 1/2. So here's the thing. For the truncation part, or a point mass, we have good revenue per sale. The revenue per sale is exactly opt, basically. But the sale probability is kind of small. It's only 1/2. Okay? Now, if we kind of scale down the sample value slightly by some factor c, which is like bounded away from 1, then we basically double the sale probability, right? Now we sell for sure. And we only lower the revenue per sale by factor c, okay? So that's big improvement for this part. Now, of course, like the truncation is not strictly point mass, and we need c to be sufficiently small to handle all the cases, but that's the takeaway point. Now, for the strictly concave part, we show that it's at least as concave as the exponential distribution. And for exponential distribution, identity pricing is actually pretty good. It's like 0.68, much better than 1/2. Okay? So we can afford to lose something on that part. Okay? And again, by scaling down the sample value by a factor of c, we lower the expected revenue by at most c. So if c is sufficiently large, then for this part, our expected revenue is still much better than 1/2. Okay? So basically, we choose c to balance the analysis for these two parts, and then that gives us like 0.589. Okay? All right, so I think I'll skip the impossibility results. And so this is kind of the summary of our results. So for the 4 main regime that we consider, we propose a couple of new results. For the asymptotic regime, we essentially have the right answer for both MHR and regular distributions. The sample complexity for regular distribution is 1 over epsilon cube, and the sample complexity for MHR distribution is 1 over epsilon to the 1.5. And for the single sample regime, we get some new upper and lower bound for MHR distribution. And noticeably, for MHR distribution, we can get much better than 1/2. But there's still some pretty large gap between the upper and lower bound. Okay, so there are many interesting future directions for this problem. One obvious one is to close the gap for the MHR single sample regime. And another one is how to do the pricing with more than one, but only constantly many samples. So far, our analysis and technique are quite specific for only one sample. For example, if I have 2 or 3 or 5 samples, I don't know how to do better than this like 0.589 or 1/2 for regular distribution. Of course, when the number of samples goes to very large, now the asymptotic part kicks in and we can do close to 1 minus epsilon. But with a few samples, we don't know what to do. So it would be interesting to see something in that regard, because in many practical scenarios, we have like some data, but it's not large enough so that those asymptotic regime kicks in and you can use concentration bound and so on. So it would be interesting to see some techniques here. And also, it would be interesting to analyze the sample complexity for more complicated settings. Like here, it's the absurdly simple setting of 1 buyer, 1 item for sale, right? In practice, you're interested in more complicated settings. And can we use some of the techniques we developed in this work to those more complicated settings and may potentially get right sample complexity answer for those settings? And also, like beyond i.i.d samples, so kind of having access to these priors via i.i.d samples is slightly more realistic than having closed form descriptions of those priors. But still, it's a questionable assumption. Like as soon as the bidders find out that you're using their bids to design future auction, they may play around it, and also like there might be like small changes in their prior every day and so on. So it would be interesting to see if there are some more realistic settings where we can still develop interesting sample complexity lower and lower upper bounds and algorithmic questions as well. Okay, so that's all. Thank you. Yeah.
When you say constant number of samples, is it not clear? The algorithm should be clear. Okay? It should be the same thing, no? You expect different algorithms.
What is the same thing?
Yeah, what's the same thing for constant number of samples?
Okay, I just think of this as my distribution, as my empirical distribution. And then I know what to run. I just pick one of these prices and I calculate if this was a...
Okay, so...
just think of this empirical distribution, right?
So that's one potential distribution, especially for regular. For regular, I think that might be the right algorithm. But still, even for that algorithm, we don't know how to analyze it to show that better than 1/2 approximation until like the number of sample gets really large. And second of all, for MHR, like this work seems to show that you want to scale down the sample value by some factor, and that helps the analysis, right? At least with one sample. So how do you do that when you have multiple samples? Do you kind of compute the empirical best price and then scale it down, or what do you do? So it's not clear. So there's some also algorithmic question there as well.
Yeah, I think even for regular, you might want to do something like that, because if you the error on either side is asymmetric. It's better to err on the lower side than to err on the upper side.
So underprice only kind of hurts your revenue by a little bit, but overprice can go from up to 0. So in that sense, you kind of tend to underprice when you don't have enough information.
So you also mentioned that for regular half is the best deterministic.
For deterministic.
So can you say a little bit about?
Oh, so that's actually very simple. So first of all, since point mass is one specific regular distribution or something close to point mass, so for deterministic algorithm, you don't want to overprice. Basically, if you overprice, then you're doomed for point mass. Now for this equal revenue curve that kind of peak at quantile equals 0, kind of underpricing always hurts, right? Because basically the optimal revenue is achieved when the price goes to infinity. Now, if you never overprice, then for this distribution, you can get at most 1/2. And identity pricing gets you that 1/2. Yeah, but of course now you know that if you use randomization, you can do like 0.5 plus epsilon. So.
But can you? Like, or is that?
That's also like one of the new results in the coming EC.
That one can.
Yeah,
If
yeah.
you use randomization, even for regular, you
Because it's
get
regular,
slightly-
okay, you know the mass around it as well.
Right.
Yeah,
But,
so you can do better than the deterministic.
Yeah.
So there's still a gap between the lower bound and the upper bound for even asymptotic samples, right? For regular. The lower bound is 1/epsilon cubed, and the best known algorithm is.
Oh, so it's off by a log 1/epsilon factor. For all these, both regular and MHR regime, it's off by a logarithmic factor.
Okay.
But the main terms matches.
But so do people in information theory know? So because I understand that now you have two distributions and you say, well,
Right.
okay, like, no, they're very similar statistic-wise, and
Right.
that's how you get your lower bound. So do people in information theory, can they do this if they have more distributions? Because to get the log back. Does that make
Oh, okay. I see what you mean. So you're saying that maybe like
So
logarithmic many.
can I differentiate? So can I get a lower bound by not being able to differentiate between a logarithmic number of distributions?
That's a good point. I haven't tried that. So that's
But
potentially one way to get there.
theory, do you know anything about that?
Oh, there's definitely like literature like doing this. Like if you have m potential classes and you want to do the classification algorithm, like then what kind of condition you need, and some other type of conversion. This is KL divergence, right? And then for multiple classes, some other type of divergence is needed. But I don't know the literature well enough to answer you right now.
For alpha regular distributions, this scaling down work, and what kind of improvements you get?
I don't know. We haven't tried that actually, because even for this one, like our analysis and technique are quite like primitive, and we don't think that's the right analysis and right algorithm yet. So that's why we didn't like try to extend it to alpha regular, but I would say probably like scaling down still helps. And okay, so now I remember I thought about it a little bit, so we can definitely.
Only in the extreme case of alpha equals 0,
Yes,
that is
yes.
the equal revenue.
So let me say the following. So all the technical lemma we use for MHR and single sample regime has a counterpart for alpha regular distribution as well. So I'm pretty sure we can get something like 0.5 plus epsilon. But what's the number? We don't know. And probably the dependency on alpha is not very good as well. So we never really figure out the answer.
This 0.68 is from exponential distribution.
Yeah. That's very. Oh, okay. So there's a simple proof of like this is for E over 4, basically. This is E over 4. But basically, identity pricing achieve E over 4 for exponential distribution. And then essentially the same argument for the regular case, right? So again, point mass is a regular distribution, so you don't want to overprice. And then you can kind of show that if we don't overprice, then identity pricing gives you the best approximation ratio for exponential distribution, and that's E over 4. And there's a slightly more complicated version, give you something like E over 4 minus some small constant. So yeah, so your intuition is right. That's from exponential distribution, kind of.
Cool, thanks.
Okay.